Well, thank you for this very kind introduction. Indeed, I have been working in the field of complex oxides already for a few decades or so. Actually, I started in the early 90s already. And what I want to do today is to, after an introduction in the growth of complex oxides with pulse laser deposition, and I also will share a bit of my history there. I want to go into the epitaxial integration of these complex oxides with silicon and 3,5 materials, but then actually focus on the materials for electronic and microelectromechanical systems there. So also quite happy to see the first talk on MOCVD. There are some similarities here. Of course, we use more an academic tool, pulse laser deposition, but on epitaxy and everything that's connected to getting the right composition and the right structure, I think there is a huge overlap there. But let's start. Well, a lot of work I will show is done in my group and with lots of collaborations, but I will specifically mention the people outside my group. So, for instance, in the University of Antwerp, in the electron microscopy for material science, the IMAT group, especially Nicolas Gauguelin, who did most of the TM or the cross-section electron microscopy work, and Rick Groenen, he was one of my previous PhD students now working at TSST. For those that do not know, let's say Twente, University of Twente. Twente is actually a region, and we are very close to a city called Enschede, which is in fact very close to the German border and only very short distance from Amsterdam. We are a technical university with also social sciences aboard. We are relatively small, around now I think around 11,000 students. But we have 5 faculties, and then important, we have a few research institutes, and the one I'm representing is the Nanotechnology Institute Mesa Plus. And what is very interesting is that we have, well, we are the only campus university in the Netherlands. So it's quite nice to live here and to work here. And we are very close to a business and science park. So a lot of companies that are spun off of the university find this place now very close to our campus. Okay, just a bit of an outline. Like I said, I want to introduce the field of complex oxide epitaxial heterostructures and pulse laser deposition. And then I will go to 3 applications. The one on piezo MEMS using silicon on insulator technology. Then I want to show a little bit of work what we are currently doing by epitaxial integration of lead zirconate titanate, which is a ferroelectric and piezoelectric material on gallium nitride for high power applications. And I also want to show an application for an application for XUV or EUV lithography, where we work together with ASML within the Netherlands and ZEISS in Germany on a wavefront corrector for lithography applications. What is the situation nowadays? So if you look worldwide, I think there are many groups that worked on complex oxides and epitaxial growth of materials. And here are 3 cross-section images of materials that we have grown in the last 20 years or so. It's only 3 of them, where on the left-hand side you see an artificial ITC superconductor, which is a superlattice out of barium copper oxide and strontium copper oxide. And what you can see here is indeed that you have epitaxy. And you can see from the color difference, or at least the contrast differences, the difference in barium and strontium. And you clearly can see that you have this, well, artificial layering in this material. And this artificial material becomes superconducting. Well, in the last 2 decades or so, worldwide, there was a lot of work going on interfaces between 2 wide bandgap insulators, lanthanum aluminate and strontium titanate. Because of electronic reconstruction on this at this interface, you are able to dope this topmost titanium layer, and you get a 2-dimensional electron gas with fairly high mobility. So it's still quite an interesting field. and still a lot of people are working on it. But you clearly can see the epitaxial relation of the lanthanum aluminate, which is the top layer, and here the interface, and to the strontium titanate. And some work that we did in the last, let's say, 5 years or so, is also working on these complex oxides. Complex oxides, I will later on show that. The symmetry is also being determined by the oxygen octahedra surrounding the B site. I will explain that a bit more in detail later on. And by tuning this symmetry, you can also tune the properties of these complex oxides. And this is what you nowadays can do. I think there are many groups worldwide now that are able to produce such nice epitaxial structures and show functional properties in these materials. But let's go a little bit back. I started in the high TC superconducting era, so to say. So in the late 80s, as you might know, high TC superconductors were found, and Bednorz and Müller got a Nobel Prize for it. Now later on, based on this work, rare earth barium copper oxide was invented, or at least was synthesized and shown to be superconducting with a superconducting temperature above liquid nitrogen boiling temperature. And that really shocked the world, I think, in material science and physics and chemistry, because a lot of groups embarked on this topic. As we did also in Twente, and I was then just a student, I was starting, and I know that I have been working on sputter deposition and pulse laser deposition on these materials. And actually what you can see here in this picture is the morphology of a grown layer of yttrium barium copper oxide made by pulse laser deposition. And actually what you can see are growth spirals. So you clearly can see that these islands are made out of spirals. And actually every step that you go down here in this growth island is exactly one unit cell layer of this high TC superconductor, which is close to 12 angstroms or so. So what you could see is actually that you have epitaxial growth, but for a lot of applications, these growth islands and also related defects at the growth edges played an important role in the properties. And at that time, also within European projects, and I will not go into too much detail, but we were working on making rapid single flux quantum logic. And again, I will not go into the details there. But in principle, you can make very fast electronics with these superconductors. And we were already able to make a rather complex structure of these thin films and make Josephson junctions and get them into circuitries like shown over here. And actually, this is an electron microscopy image of the top of such a rapid single flux quantum logic device, where you actually can see that it works. So we could make integration up to, let's say, 10 to 20 of these Josephson junctions. But you can also see a lot of, let's say, some defects. You can see some particles there. And we also knew that further integration was quite difficult, because the reproducibility of getting the right properties of the individual junctions was very, very difficult. So every now and then you were lucky and you had a working device, but it was quite difficult. So at that time, I started to do more and more research on the growth of such complex oxides. And already in these early days, and we are still talking about, let's say, 25 years ago or so, most of these materials were grown on perovskite materials, single crystals of strontium titanate. And well, we got our first atomic force microscopes at that time, and we were looking more and more in detail. Okay, what is the surface finish of such substrates? So we were used already to these nice pictures from silicon, where they use tunneling microscopy and see these nice step terraces, A and B type step terraces on silicon. And this is actually what we saw with strontium titanate. And although I show only 3 pictures, that was a lot of work going on there. So what do you see here? So if you have a single crystal and you have to cut a wafer out of it, then of course you try to cut it well, very close to a high symmetry plane. So for instance, in the one direction. But of course, you can never manage that completely. So you always have a little angle between the topmost layer and the surface of the crystal planes. And so what you can see here, so if you look, I will get my laser pointer on. Yeah. So if you look here at this picture, you clearly can see a step terrace-like structure. So every time you go down, you expect something like a unit cell layer in this material going down. But at that time, we also did lateral force microscopy. So with the AFMs, you could also measure the lateral force, so the friction of the tip with the surface. And we clearly saw two types of contrast. In this case, you can see the bright and dark. And we have looked more in detail there, and we also annealed substrate, and actually we could clearly see these two types of surface finish. And well, knowing that strontium titanate is made out of strontium oxide layers and titanium dioxide layers, you might already envision that part of the substrate would be covered or terminated by strontium oxide, whereas the other one is titanium dioxide. So, and actually this is true. So this lateral force will give you the contrast because of the different chemistry at the surface, being strontium oxide and titanium dioxide. Well, then let's go a little bit back to the perovskite structure. There are many ways to show this structure. So this high TC material, but also the strontium titanate belong to the perovskite structure. And one way to envision this is that you have an ABO3 structure where a octahedron of oxygen is surrounding the B cation, and in between these octahedra you have the A cation. You might also look at a little bit different way. So if you look into planes, so if you cut this titanium oxygen plane, which would be then, if you look from the top, would look like this, where you have the B side and the A side oxygens. And if you would cut it through the A side, you will get a surface like this, where you have A side and the oxygen ions over here. And actually you can see this unit cell layer as a stack of BO2 layers and AO layers. So in the case of strontium titanate, you would have titanium dioxide, strontium oxide, titanium dioxide, and then of course, again, strontium oxide. And the beauty of this system is that the lattice parameters are mainly being determined by the oxygen network. So oxygen ions are big. So actually the representation, what we typically do in textbooks, but also in literature, is quite wrong. So these oxygens are big, and you have a closed packing of oxygen ions there, where at some position oxygen is kicked out and you have strontium, and in between the pockets of these oxygens, octahedra, you have the smaller B-side ion. But because of this oxygen backbone, you can have perovskite materials where the lattice parameters are very similar. So here I sketched a few: lanthanum aluminate, a wide bandgap insulator. There the A parameter is close to 3.8 angstroms, strontium titanate 3.9, strontium ruthenate, which is a metallic, ferromagnetic metallic oxide, 3.93, and lead titanate, which is the basic structure of lead zirconium titanate, it's 3.9 angstrom. And because of this oxygen backbone, it's relatively easy to stack them on top of each other as you were playing Lego with Lego blocks. And this is quite interesting, because then you can do it. But let's go a little bit back to this substrate. So we thought already, okay, we wanted to get rid of this mixed termination. And again, here you can see a sketch of strontium titanate, where you would have strontium and titanium dioxide layers. And actually you want to have a clean single atomic termination layer there, for instance, completely titanium dioxide. And well, there was a lot of work going on in Japan at that time. So Masashi Kawasaki was doing quite a lot. So he first showed that you can get this trick with HF etching, you can get rid of the strontium oxide. We later on worked on it, and we revised kind of his methodology into our methodology. And with that, you can get very clean strontium titanate surfaces. So this is again an atomic force micrograph image of strontium titanate, where you can still see the steps going down. You have one terrace, and then you go down to the next terrace, where you have a step of a single unit cell layer, and this is completely single titanium dioxide terminated. And if you want to have it strontium oxide terminated, you just deposit a single monolayer, and you still have this stepped surface, but now with a different termination. And that was actually very important in this field, that we control. If you want to do epitaxy, if you want to do this atomic control, you also need to have this substrates atomically controlled. And these are just a few examples from our group, but also other groups, that if you, for instance, grow strontium ruthenate on top of this strontium titanate, well treated, well, this is actually a 50 nanometer thick strontium ruthenate layer, and you clearly can see still the imprint of the substrate, and the 50 nanometer thick strontium titanate is atomically, strontium ruthenate, I have to say, is atomically smooth. If you still have some leftovers of this other termination, and this was a somewhat thinner film, only 6 nanometers or so, clearly you can see the effects of this different growth at these different terminations. So this treatment is very important. And nowadays there are many other materials that can be treated in a similar way, whether it's aluminate or a scandate or another oxide substrate. So it changed this field quite a lot. So I'm going to be focusing on pulse laser deposition. This is the main technique that we are using nowadays for our complex oxides. And for those of you that did not see it, compared to MOCVD, it is different. So you had this lecture on MOCVD, where you use chemical or gases to get the right materials inside your reactor. In our case, we use a target of a certain material. So, for instance, if we want to grow this high TC superconductor, we press a target of this material. We shine an intense laser on top of this target, and because of the interaction with the laser and this target, you get evaporation, and this evaporated gas contains now the species which are in the target, and they are translated and expanded in this high intensity plasma towards a substrate, and then this material, of course, can be deposited on top of a substrate. And if you do it at the right temperature, in the right oxygen pressure range, and here are typical ranges for temperature and oxygen pressures for the growth of complex oxides, then you can get epitaxial growth. Well, we developed at that time high pressure read. Of course, read was already there. Electron diffraction, again, I will not go too much into detail, but with read electron diffraction, you can monitor the growth. You can get from the surface, you can get information about the crystalline quality, but you also can use it as a growth monitor, because you will see oscillations when you have atomic scale growth. And I will show an example later on. And the high pressure means that we are able to operate this electron diffraction up to 1 millibar, which was at that time quite high. It was limited to, let's say, UHV or somewhat higher pressures. But now we could also use it in typical PLD settings. And just for your knowledge, of course, there are many other systems available, molecular beam epitaxy, sputter deposition, but also chemical deposition tools like ALD, atomic layer deposition, that can make these complex oxides nowadays. And well, if you just go a bit into the growth of pulse laser deposition, and this is a very schematic view, excuse me for that. So we use lasers like excimer lasers. Excimer lasers have very short pulses in the range of 25 nanoseconds or so. And if you have a single pulse irradiated with a high intensity on top of this target, then of course you get what we call ablation. So you ablate material from this target. This ablated material forms a high pressure gas that is just in front of the target, and because of the pressure difference of this high pressure with the vacuum, this gas starts to expand. And when it expands, it also the species will hit the substrate, and you get deposition. That takes, of course, more time. So that's why these deposition pulses are a little bit longer than the laser pulses. Laser pulses 25 nanoseconds. Typical deposition pulses are in the range of a single microsecond or so, a few microseconds. So you get a very fast deposition, a very short pulse. And actually what is nice about pulse laser deposition, that because of this very fast deposition pulse, you actually increase the supersaturation at the surface of such a substrate, which makes that you have a, the driving force to get from the gas phase to the solid phase is very high. So you get a very high nucleation rate on top of the surface, or a growth there. And of course, in between the pulses, there is no deposition. Then this supersaturation drops until the next pulse is coming. And this is quite special for pulse laser deposition, meaning that we also can deposit materials that are very volatile. And this is very important for this talk, because I will talk a lot about lead-containing materials. And lead is very volatile at higher temperatures, but because of this driving force, which we call supersaturation, you can transfer the gas from the gas phase to the solid phase quite fast, and that makes that you can get this epitaxial growth at higher temperatures also on such materials. Well, just one slide on reed. Here you can see this oscillatory behavior of the growth. So every time the intensity of the reed is maximum, you have deposited exactly one single unit cell layer. And very interesting, you can also see every individual pulses there. And again, there is a lot of growth kinetics into it. I will not go into detail there, but we learned quite a lot from the growth kinetics from looking at this reed data there. And maybe this is more interesting to show this movie there. Here you can see strontium titanate growth on strontium titanate. Here, actually, this is the real reed data. So here you have deposited a single unit cell layer. This is Monte Carlo simulations based on the measurements we did on the kinetic parameters. We plugged it into a Monte Carlo simulator, and we got this movie there. And this is actually a very nice growth mode, because you get a single unit cell layer by layer growth, and you only get new nucleation when the previous layer is completely finished. So what you actually can see here, so we are at the maximum of this intensity. If we stopped here, we have exactly deposited 4 unit cell layers, and that is quite interesting. And with this technique, this is a typical system as we use in our lab. So this is really a lab-based PLD machine, where we have combinations with pulse laser deposition, also with in-situ measurement techniques like photoelectron spectroscopies. We can also do diffraction with that, connected AFMs, STMs. Actually, this is a somewhat older picture, because we have now some new tools connected to it, and also a small MBE tool for other materials. So, and this is what you can see in many labs now around the globe. If you can do a single, let's say, material, then of course you can select more materials. And in our case, we put it on carousels. We deposit these materials. We exactly know when to stop every individual material. And with that, we can make these superlattices, as shown, for instance, over here, where this is a superlattice of a manganate and a titanate. Again, I will not go into the details there, but you can see this, the growth direction, and you can see this atomic scale growth. And and this is actually how we make those materials that I have shown just before. These are the technique used. What we have seen, and again, I saw again similarities there with the previous talk, that when you do this kind of depositions and you think, okay, you have this your target material, whether it's a gas in MOCVD and control the stoichiometry, or we do it within the target. Of course, if you want to make a material like lanthanum aluminate, then of course you need to have the right composition in these materials. And this is not so easy. You really have to tune the parameters in order to, for instance, get the right composition ratio between lanthanum and aluminate. You can easily, if you do it a bit wrong, you can do it. But what is very important is that oxygen is, of course, a very volatile species, and it is, you cannot just get a target material and you get this kind of composition and you transfer it. You lose most of the oxygens from this target. So you need, let's say, to add oxygen during the growth. And we do that because of this oxygen pressure inside the PLD chamber. And without going into too much detail, these are these two-dimensional electron gases. Here are the mobilities of the electron gas. And the takeaway message from this picture is only that here you can see the background gas of this during the deposition, ranging from 10-3 to 10-6 millibar, and clearly you influence the properties of these materials. And actually, this is very clearly seen in these two-dimensional electron gases, but in principle, you can see that in every deposited material. And so we did quite a lot of work on understanding this process. So here you see movies of light-induced fluorescence and self-emission from the plasma while ablating material. In this case, it was strontium titanate. And if you just focus on this plot over here, you can see the light-induced fluorescence data of titanium. So when you deposit or when you ablate from a strontium titanate target, then strontium titanium gets off, and actually this is the signal from the metallic titanium species. But what you can see here, and this is an intensity spot, that eventually the titanium gets lost, because if you go further away from the target, there is no titanium anymore. It's not lost, but because of the oxygen background, it is being oxidized in the plasma. And we know nowadays that this oxidation is very important for getting the right material there. So this light-induced fluorescence, and you can see it here, because here we used a somewhat higher pressure, you can clearly see that the transfer from titanium into titanium oxide goes much faster. And I will skip this slide. I will keep it in for later on. But with the self-emission, you can already see that depending on the pressure you are using, you get either more metallic species or more oxidized species. And that's quite important for getting the right materials. So this was a relatively long introduction into pulse laser deposition and what we do nowadays. But it's still important for the remainder of the talk on the PZT materials, because even when you translate it to to silicon or to 3.5s, you still want to have these composition control and epitaxy control, and that's you have to have additional tricks if you are not depositing the material on best, let's say, epitaxial substrates or so. So where are we standing now? So here you can see again the tool that I showed before. This is a really lab scale tool. Nowadays there are also tools available for pulse laser deposition on this is 200 millimeters, but nowadays also the first test has been done on 300 millimeter wafers with cassette loading. This is a somewhat older design. Nowadays, it's also comparable to what was shown in the previous talk. So with cassette and the central loading tool that can load the samples into the PLD chamber. But what is very important that we now are able to, well, not only work on a few millimeter scale, but also work on wafer sizes up to 200 millimeters or even bigger. So in our lab, we still stick to this 150 millimeters and 200 millimeters, but now we are in the range that we really can work on real devices and work more actively with companies. And one of the main things that we do is by using this lead zirconium titanate, which is a perovskite piezoelectric material. If you grow that on top of a thin membrane of silicon, and we do that by using a silicon on insulator technology. I will get into that later on a bit more schematic. How do we make such layers? But because of this bimorph actuation, so you have this capacitor-like structure of the PZT, which is clamped on the silicon membrane. If you then put a voltage across this piezo layer, it tries to extend in the C direction, but also to contract in the AB direction. But because it's clamped, you get this bimorph actuation, and you can actually make such membrane move there. And actually, we are working quite actively together with Canon printing company to work on these piezoelectric materials for print heads, because these are the basis of print heads for inkjet printing. But you can do more. So you can make these moving membranes. You can make moving cantilevers or bridges. And actually, this is just a few people that we have been working on. OC is now part of Canon. We have been working on piezomechanical ultrasound devices. We have been working on energy scavengers. We have been working on biomems applications, so making e-noses. And I will briefly touch upon that with Philips and some other companies there. So just to show one of these applications, and this was done with the Amsterdam Medical Center, and we worked together with Rianne de Vries and Professor Peter Sterk on this. And they were already working on breath analysis to detect diseases. And actually, Rianne is almost finished her PhD, and actually she now also used the same breath analyzer to also being able to measure COVID, by the way. But in this breath analyzer, there are sensors that are also being used in the automotive industries. And if you now look at patients, for instance, with COPD or lung cancer, so serious lung diseases, and if you now look at all these sensors that are inside, and if you do principal component analysis, you clearly can, they improved it, but you can discriminate between diseases there. And the basic idea is there, if you have a disease, a lung disease, if you have inflammation there, then of course also molecules are being produced that are not belongs to your body, so you exhale them, and if you can measure them, then this tells you something about the disease that you have. The problem with the current sensors are that the chemical information is completely lost there, and we need higher sensitivity and specificity. And this is actually what we have been working on together with them. So we have been fabricating very small, let's say, cantilevers based on this piezo silicon membranes. Here you can see one of them, very thin. And what we can do is we can actuate it. We can make this move up or down. And with that, it becomes a very sensitive mass sensor. So what we did is that we use this as a transducer, because we have put here different molecules on top, which then could act as an anchor of biomarkers, whether it's fractions of volatile organic components or even DNA fractions. We can use this as a very sensitive mass sensor. And because of different chemistries, you can make it blocking or less blocking, and therefore you have more chemical information. And actually, this is also worldwide a very active, let's say, technology done by a lot, and people have even shown that you can measure single molecules with such technologies. Well, how did we do it? We used this piezo MEMS technology. Here you see the chip completely made, where you have this silicon membrane, and on top of that, this piezo capacitor on top of it, and you can make it vibrate, and with that you can measure it, the mass. It's like a mass sensor. And here you can see the fabrication process. So you start with the silicon on insulator, you deposit the first electrode, you pattern it, you deposit the PZT and the top electrode, you pattern it again, you pattern the PZT, then you put gold on top to get better contact to your top electrode. And now it's time to start to process the backside there in order to get rid of the silicon wafer, so to say, and only the membrane is left over. And you have this freestanding membrane there, which you now can move. And this is well done in our lab. Actually, I did not show any data there. We are still working on that. But we have seen already that such devices can have the right sensitivity there. So now we have to make the next step there. I started off with epitaxy. Well, in the field of piezoelectric materials, there are many deposition techniques like sputter deposition or more chemical deposition techniques like salt gel ways, and there are different ways to look at it. And I think all of the techniques have matured nowadays, and this is also what we have done. So if you focus on the pulse laser deposition, and this is now the remnant polarization of these materials while cycling it. So imagine that you have this resonant cantilever, you cycle it up to 10 to the 10th times or even longer. Because of mechanical wear or also electronic wear, typically you will find that the properties will deteriorate after some time. And this is typically related to defects inside your material. And if you increase or decrease the number of defects and you increase the crystalline quality, and this is what we did with this epitaxial growth using pulse laser deposition, you can actually show that there is no fatigue or aging of this device at all. It was interesting to see that, and this is still on small scale, so with our PLD systems done in our labs, we can make this quite good in the sense of stability, low defect density, and no fatigue, as you can see over here. Actually, if you would take such a resonator, and this is done with a vibrometer, we let it also resonate up to the 10 to the 10 cycles. And if you would measure the tip displacement, you also can see that the tip displacement does not show any signature of piezoelectric deterioration when you use it there. So epitaxy is quite important. But of course, we need integration with silicon, we need epitaxial growth, we need orientation control, and very important, we need strain engineering. And this is also why I was a little bit long in the introduction, because I hope that I showed you that this integration and epitaxial growth is very much related to already the initial growth and the control of the species that you are depositing. And by the way, here are a few examples of early work on metallogenic CVD that connected to the previous talk, but also sputter deposition of these materials. So there are more ways to do it. Well, if you talk about epitaxial PZT on silicon, and this is a schematic sketch, what we wanted to do is to get a complete, fully oxide heterostructure on top of silicon. So I've shown you in the first few slides that you have strontium ruthenate, which is a metallic oxide. So it's an oxide perovskite material, but it is a very good conductor. And you need that for this parallel plate configuration. And you can get epitaxial growth of strontium ruthenate, lead zirconium titanate, and strontium ruthenate. But this is very easily done on an oxide single crystal, but it's not so easy to do it on silicon. So you need a buffer layer there. And this buffer layer should avoid any diffusion and reaction of the silicon or the silicon oxide with the layer that you put on top, but it also should, you should have crystalline growth through epitaxy. So we have to use the crystalline quality of and the orientation of the silicon substrate, then deposit the buffer layer, and then get to the oxide growth there. And what I will show mainly are two ways to do it. This is with yttrium stabilized zirconia cerium oxide buffer and nanosheets. We also did strontium titanate, but I will not go into that, maybe just a little bit. So what do? You have your silicon substrate. We deposit, let's say, a YSC buffer layer, and this is not so easy. So this is already an oxide. You have to grow it on silicon, which is very easy to oxidize. And what we do, and this is a trick that was already shown in the early 90s, that if you deposit zirconium oxide or zirconium in a reduced environment, it will oxidize and grab the oxygen from the silicon oxide layer on top. And actually, this is a cross-section TM image of already some time ago, where you clearly can see epitaxy of this zirconium oxide layer on top of silicon. And there might be some regrowth of silicon oxide over here, but you clearly can see this, and also in this diffraction pattern, you can see the crystalline epitaxial growth of this material. We use a cerium oxide buffer layer in order to control the lattice parameters. You can see here that these are two fluoride oxides. They have lattice parameters very close to silicon. YZ is a little bit smaller, but here you can do the scavenging trick, not with the cerium oxide, and here we are back to this cerium oxide layer. And then we have to deposit this strontium ruthenate PZT and strontium ruthenate electrode. Yes, and what we saw actually was something like this. So we made this material, we broke the sample and looked with electron microscopy to the sites, and we clearly could see epitaxial growth. Yes, that was good, but we clearly could see this very this grain-like growth there. So it worked. So the devices worked, but there were still many defects there, and the crystalline orientation is not okay there. So and later on we found out why. Because if you look now to the lattice parameters, as I shown before, the cerium oxide and silicon is cubic. Strontium ruthenate, which we use and the PZT is also cubic, but with a much smaller lattice parameter. And if you have this cube on cube type of epitaxy, now you can have two ways to make it fit. One way is to rotate the cube in the plane, and actually that would have a nice fit in two directions. But the cube can also rotate out of plane, which is sketched over here. And now if you take, let's say, this value and you multiply it by the square root of 2, actually you get very close to this value. Whereas on the other direction, of course, it's only this 4 angstroms there. And if you would rotate it in the plane, then you would get a very nice fit with this, or almost perfect fit with this silicon. And actually, still, the material wants to grow in this fashion. So if you just continue the growth as I showed before, you get this 110 type of growth there. And nowadays we have tricks to get into this type of growth. And this is done over here. So and again here we use the trick of single monolayers, because here if we do not do any trick, we clearly get this PZT 110 growth on this 001 oriented fluoride, and therefore also silicon, you can see over here. But if we do an initial strontium oxide deposition, and we do that a little bit with a trick, that doesn't matter, but we have only strontium oxide, a single monolayer, and then we continue the growth, we actually see a clear 001 oriented PZT, 001 oriented strontium ruthenate on top of this material. And here the chemistry is quite important. So the chemistry determines in the end this epitaxial relation there. So here 110 with some additional angles of this 10 degrees. And here you can clearly, from the rocking curves in X-ray diffraction, you can clearly see that it's 45 degrees rotated in the plane, and you get epitaxial growth. And that was quite important. I also talked about strain. And here again, like was there's a similarity with the talk just here before. If you do gallium nitride, for instance, on silicon, because of the difference in thermal expansion, when you cool down the sample from growth temperature to room temperature, you have different thermal expansion, and then you have additional strains inside the film. And that's also true for PZT. So this is a plot from Landau theory where you can see temperature and strain. And we grow typically at 600 degrees, and where the strain is completely relaxed. If you then cool down, you can get into many different types of phases there, where the symmetry of the PZT is then very different. And actually, we are also now looking into getting different strain states and compositions in order to change the functionality of these materials. But be aware that different growth temperatures with different thermal expansion coefficients will get you additional strains in thin films, and sometimes they are unwanted, sometimes they can even enhance your properties. Well, like I said, we have this thermal expansion. We grow rather thick films of the PZT, so we do not think that we have still, let's say, this strain because of the lattice mismatch, but it's mainly thermal expansion. And well, if the thermal expansion coefficient of the substrate is larger than that one, in this case of the PZT, when you cool it down, that means that the substrate will shrink harder than the PZT. And so because of the clamping, you will get compressive strain. So you get this milk can type of distortions. And in the other one where the thermal expansion of the substrate is smaller than that of the oxide, in this case PZT, you get tensile type of distortions. And for silicon, the thermal expansion is much smaller than that of oxide, so typically we have tensile strain in the films. We have been looking into that a lot, and also looked into the properties there. Well, actually here you see an X-ray lattice parameters determination of the bulk piezoelectric material, cubic at high temperatures, and then it gets into, for instance, in this tetragonal phase, when you have some composition. If you clamp it, it will still get this tetragonal phase, but with different in-plane parameters, and therefore different properties there. And here again, this is now some also Landau theory done by Petsev. And actually now you can use this trick of using different substrates to change the material symmetry there. So this is what we did. We selected a few substrates with different thermal expansion coefficients, and we grow at high temperature, cooled it down, and because of this different thermal expansion, you get different in-plane strains there. Without going in too much detail there, this is again the misfit strain versus the content. We are close at 0.5, so we are in this range there. And well, here are all the substrates, so scandids, tantalite, zirconiates, magnesium oxide, silicon, etc. So we used many substrates with different thermal expansions. And to make a long story short, I will go a bit quick through these slides. We could make all these epitaxial films, and from the PZT position, you can see already that they have different strain states. We did the reciprocal space mapping in order to measure the real strain state. And with that, we understood that we are changing the strain of the materials, and we changed the symmetry there. And with that, we got very different, let's say, properties here. So for those that know a ferroelectric loop, so this is polarization, excuse me, this is polarization axis, and this is electrical field. But you can clearly see that all these films, they are exactly deposited in the same deposition conditions, but because of the clamping, you get very different properties in the electrical field. And this is quite interesting nowadays. And well, this is ferroelectric behavior. This is the piezoelectric behavior, and we can clearly change the properties of these materials. And this is well the relation towards theory. Because of time, I want to skip this slide there over there. So what I wanted to show in this part is that, let's say, well, you can have this epitaxial growth of these smart materials PZT on top of silicon. The crystalline growth is very important on the properties, and this is also sketched over here, polycrystalline film versus an epitaxial film. And clearly the piezoelectric properties and the functionality, so tip deflection, for instance, are very much determined by the crystalline quality of such films. And composition is also important there. This is now with niobium doping, and you can change the properties there as well. We went into this well, so-called figure of merit for energy harvesters, and by controlling the epitaxy and controlling the composition, we actually we can get quite decent materials for use in energy harvesters, where this is the well, the piezoelectric properties there, and as you can see here, compared to well, typical PZTs, we can have now much higher values because of this control. I want to switch gears because I do not want to take too much time of you. I think this is interesting to show. Another application, this is on power field effect transistors using gallium nitride as a 3,5 semiconductor. Well, gallium nitride is being used in power FETs a lot. And the takeaway message there is you want to, well, use a switch as a switch for high power, for instance, in controls of batteries or any other type of applications. So what you need is, when the switch is on, you need a very low resistivity, but you also need a very high breakdown voltage. So that means that these are the two most important parameters for such a high power field effect transistors. And if you look at the breakdown voltage, this is just one example. This is mainly caused by the breakdown in the gallium nitride. And this is being sketched over here. So this is a typical FET type of structure. If you put high voltages on the gate, you can get electrical peaking of the field inside the LGAN over here, and you can get breakdown in this gallium nitride. Well, one way to circumvent it is to place a good conductor for electrical fields on top, which is a high K dielectric. And that is what people already did, right? Like silicon nitrides or other materials. And in this way, you guide this high field or this electrical field away from the LGAN. And in this way, you can put a much higher voltage on these gates. Well, silicon nitride is nice, but we worked on this in oxides, and the dielectric constant of these oxides is very high. So it can be a few hundred or even over 1,000 or so. So we got together with electrical engineers and also with companies, and to see would it be possible to grow this PZT, which is being used as a piezoelectric material, would it be able to grow that on top of such 3,5 semiconductors? And this is what we did. And now this is a complete different story in terms of crystalline quality. The gallium nitride has a very different crystalline structure compared to this cubic perovskite PZT, which I showed before. And if you would, well, sketch the best fit, then you would have something like that you, well, put this cube on one of its tips and get it to the 111 direction. Still, it has a fairly large mismatch, around 11% or so. So you need to, again, to do something on buffering, first of all, to avoid chemical reactions, but also to get the right stoichiometry. And in this case, we used magnesium oxide also in the 111 direction. And although the misfits are, or the mismatches are very large, you can clearly get this epitaxial relation in real films. This is what we did. So this is the magnesium oxide on top of this gallium nitride, and then here the PZT. From the X-ray diffraction, we can see that we have epitaxial growth on top of that, but you need magnesium oxide, and even a single monolayer of magnesium oxide can already get this epitaxial growth. If you do not have this single monolayer, then you do not get epitaxial growth. So here again, single monolayer growth is really important for the initial stage of the growth there. It's ferroelectric, so you see a PE loop. We measured these properties in more details, not so important for now. We also got into, let's say, the crystalline quality. So here are reciprocal space maps, and you can clearly see from the in-plane lattice parameters that all these materials are already relaxed. And that is very interesting because that's very different from what we are used to know. Because if you now look with cross-section electron microscopy, so here you can see the gallium nitride and the AlGaN over here. We used 3 nanometers of magnesium oxide and PZT on top, and here you can see it much larger. So you can clearly see epitaxial relation between the gallium nitride and the PZT, and the interfaces are very clean. So you hardly see any interdiffusion there. This is also what we measured with EELS mapping, so electron loss mapping. So within the measurement limits of the EELS, what was done in Antwerp, we did not see any interdiffusion there. And what was very interesting, if you look carefully to the in-plane lattice parameter, you do not see strain or relaxation, but already from the very first layer, the in-plane lattice parameter, which is sketched over here, it makes a jump to the bulk properties of, in this case, the MgO and the PZT. And actually, I have never seen such kind of growth before. Probably it has to do something with the nature. The oxides, of course, have a lot of ionic bonding, whereas the gallium nitride obviously does not have such bonding there. So the interface is very different. We looked into this in more detail, and actually it is quite interesting to see that 19 in-plane lattice parameters, periods of the magnesium oxide, of the GaN, fits around 20 of the magnesium oxide. And this is repeated in 2 directions. This was very interesting to see. Does it work? Yes, it works. So we do have this, we made devices out of it. This is the sketch. It works as a field effect transistor, and the first device already showed a much higher breakdown compared to the one without the PZT. And actually, this brought us also to another topic together with other companies to continue on this work. So now we are also trying to orient the PZT with different ways and to improve the properties of the PZT, because like I said, we have now only the 111 direction, but we also want to go in other directions. So we are playing with other buffers there in order to improve these properties. Okay, and just now a few slides on the last application, and then I think I will stop because there might be many questions, and I'm already talking for close to an hour or so. But I briefly want to mention this, and excuse me, I will skip a few slides there, but I think this is an interesting application. So I talked about fully epitaxial systems. We worked worldwide in many groups for a lot of years to get this epitaxy, to get single crystalline qualities on top of oxide substrates. Nowadays we can do it on silicon, we can do it on 3,5s. But how to get epitaxy on a glassy substrate? So how to get a crystalline film on a surface that is not crystalline at all? Well, we got into a collaboration with ASML, which you might know as a company in the Netherlands that make lithography tools for the CMOS market and other markets. And this is one of their latest designs there, where instead of using, let's say, optical elements made out of glass, they now use mirrors, Bragg mirrors. And there are many of these mirrors inside such illumination set, around 19 or so. And of course, they all have their mistakes. So they might alter the wavefront in a way that you do not want. That might also be because of temperature differences or whatever. So one way to circumvent that is to make one of these mirrors smart. And actually that we got into this project called SMILE, so Smart Multi-Layer Interactive Optics for Lithography at extended UV wavelength, 30.5 nanometers. And so here is a sketch of this Bragg mirror. So this is, these are fairly large mirrors. So the largest ones are very large, up to 0.5 meter or so, where you have this Bragg mirror made out of non-oxide materials, which act as a mirror. And you can now do this wavefront correction, so distort the wavefront of the incoming light by changing, let's say, this Bragg mirror. Well, the most interesting way would be if you could make a Bragg mirror where you can change the D-spacing. That's very difficult. You could also do some reflectors tuning if you would have two Bragg mirrors and you put something in between that can change its size. Or you can just do wavefront correction where you have patches of different smaller mirrors on top of a bigger one, where you change the wavefront, so to say. And actually, this is what we currently are working on. So within our group, which is called the XUV group, they did a lot on this Bragg mirrors, and these Bragg mirrors are made on ultra low expansion glass, so it's on glass. And be aware that these in real devices, this glass might be up to 5 centimeters thick, 0.5 meter in diameter or so. So this is quite big mirrors there. But some of them are smaller, and you can do wavefront corrections at these smaller ones. But it's glass, so that was very difficult. This just to say that we worked on this one. So this is kind of how a wavefront corrector could look like. So this is a mirror where you have these different patches. And if you look at a single patch here, you might have a multi-layer made out of molybdenum and silicon, where you have this reflection that is 13.5 nanometers. And this is on top of a piezoelectric stack, on top of this substrate, which is this ultra low expansion glass, which is amorphous. And we wanted to put this piezoelectric layer acting as a kind of a piston. So where you, if you apply an electrical field across this piezoelectric layer, this layer would move up and would distort this wavefront over there. And the way we did it are several ways. One of the interesting way we are doing at the moment is using nanosheets as buffer layer. So this is quite a busy slide. This is showing that, next to this two-dimensional, again, very nice to see the similarities there, because also the previous speakers talked about these like calcinides materials, the 2D materials. Actually, you have also the oxide equivalents of these graphene-like structures. You can see them over here. We can make magnesium oxide, or manganese oxide, sorry, titanium oxide, calcium niobates. So you can actually make these flakes of such materials, and you can see it over here. These are atomic force height maps of titanium oxide, manganese oxide, and calcium niobate, and you clearly can see the thickness of these individual nanosheets. The good thing is, of course, that these are very thin sheets and they are very crystalline. So, and there are ways with Langmuir-Blodgett type of tricks, you can make them float on top of a liquid, And by compressing this nanosheets to a dense layer, then you can use this Langmuir-Blodgett type of deposition. So you immerse the substrate completely in the liquid, and then you you take this substrate out of the liquid while still compressing this nanosheet there. You actually can grow such nanosheets on top of and here are some examples where you can see these nanosheets on top of glass. Of course, these are still flakes, but actually you can get quite good densities, and if you would do another deposition, you could also get full coverage or close to full coverage in a second layer or so. And this is what we have been working on some time now, where in this case this was a test of strontium ruthenate on top of calcium niobate and titanium dioxide nanosheets on silicon. And clearly you can see that we can have this epitaxy. In this case, this is we used the calcium niobate nanosheets on top of glass, on top of silicon. We used lanthanum nickelate as an electromaterial and PZT, and you can clearly see from the X-ray diffraction that we get epitaxial deposition on top of, in this case, glass here. So you can clearly see this out-of-plane epitaxial piece. And more importantly, you can also see the ferroelectric and the piezoelectric behavior of these PZTs on top of silicon or glass. And actually, you can get fairly high piezoelectric coefficients using such technologies. And with that technique, we can tune the crystalline quality, we can tune the morphology of such films to make it very dense or less dense. And here you see a single patch where you can still see that it was not completely covered. But here you can clearly see that with the white light interferometer, we measured such a displacement curve, and we clearly can see that we can get this piston-like behavior of PZT on top of glass. Well, and without going in too much detail, now there is a lot of things you can do. Well, if you look carefully, if you have uncovered areas, you get a different type of growth. You need to circumvent that. You can have different type of orientations depending on the deposition rate, depending on, for instance, the temperatures. So you can lower the temperature and still have decent materials. So this is also interesting for applications for backend processing of CMOS. But again, whatever you do with temperature, so this is the lowest temperatures, you still have a very nice piezoelectric behavior. Higher temperatures get higher values, but still you can do it. And this opens quite a lot of new ways to get such epitaxial systems in top of glass or top of silicon or also 3.5s and get these novel functionalities. And this is thickness dependence. I will skip this one slide. And again, there with thickness, you can also have these high D33 values there. So it's an interesting way. These are strain curves. I don't want to go into too much detail there. And that brings me to my conclusion. So I hope that I've shown you that nowadays, let's say oxide complex growth worldwide in many labs is a nice material to work on several functionalities, whether it is superconducting, magnetic, ferroelectric, for all kinds of applications. A lot of groups, also our groups, are working in the integration of these complex oxides with large-scale silicon and 3.5 technologies. And I've shown you a few samples, so sensors and actuators, high power electronics, and also piezoelectric smart mirrors. This is a nice picture actually to show, because here you can see this calcium niobate sheet and the lanthanum nickelate on top of this glass. So you can see this glassy behavior of the glass, and directly this epitaxy on top of it. And you can use it, for instance, for these smart mirrors. And a new type of research that we are getting into is what we call neuromorphic computing. I do not have time to get into that, but also there, ferroelectric behavior and piezoelectrics is very interesting in trying to make neuristor or memristor type of devices. And if you could combine that with silicon CMOS, you could think of neuromorphic architectures and make well, new functionalities, or do memory or data processing with much lower power consumption. And I think this is a really interesting new topic. And with that, I would like to thank you for your attention.
Thank you very much, Guus, for this very nice, interesting presentation. I think we can give applause to Guus for such a nice one.
Thank you very much.
Very broad and eye-opening presentation. Very nice. And let's get to the questions. I'm pretty sure there should be many. Is there anyone with any question? You can write it either in chat or ask in person. Okay, so then let me have a few. Guus, you talked about the perovskite structure that you grow. By which method do you actually grow that in your labs, or what were the methods that you tried?
Of the perovskites, you mean?
The perovskites, yeah.
Yeah, so it's mainly pulse laser deposition, but also we do a lot of pulse laser deposition, sputter deposition. We do quite a lot, and we also do sol gel processing. So we are thinking also, but that's not clear yet, to also do something on ALD, atomic layer deposition, because well, as you might know, that we work quite actively together with a few spin-offs. So also Soulmates is a spin-off. We are trying to get this PLD also out in industry. But PLD, of course, is a very new technique in industry, and that takes time. Whereas ALD might do the job. I think, especially also in Norway, they have already shown that, for instance, lanthanum nickelate can also be grown quite decently with ALD. So that might be interesting. Yeah.
Okay, thank you. And so maybe something that combines to this question, how is that with the PLD? I'm not a PLD guy, but is that, can you actually, or what's the growth speed of the PLD? Can you control the speed? As you know, as you said, it's crucial for the industry now. So
Yes.
I suppose that they are trying to push it to the limit of the speed.
Good question. Good question. Yes, it is. So, for instance, if you want to grow on a 200 millimeter wafer, a micron thick PZT or so, it will cost you like half an hour. So it is already quite fast. And again, this also fits to what I've shown before. Maybe you can remember the cartoon where I showed the pulses of the laser and these deposition pulses. These deposition pulses are very short, a microsecond or so. So, and especially for PZT, I showed you this tail in the supersaturation that goes quite fast. So every individual pulse and the growth, everything goes quite fast. So then it just depends on what type of lasers you could use. So if you have a high frequency lasers, and nowadays we use them, there are multiple hundreds hertz or so, you can, and if you combine it with the right, let's say, rotation and translation tools, you can actually change the position of the plasma quite fast, and therefore you can have quite fast growth already. I think growth is not, speed is not the issue. One of the major issues is particles, because of this very, well, this explosive ablation. If you do not have the right target material, you easily can create some particles. So, and actually that is what companies like Soulmates are really doing to get rid of these particles. And also again there, in the same as in the previous speaker, the added particles. So he always mentioned that you should have a few particles over this complete wafer. And actually, they made very nice progress that in getting rid of the particles with PLD already. So that's the problem.
Right. Thank you. Good. There have been some questions in the chat. So from Mira Koribal, is it interesting to see how DUV mirrors turned from almost impossible to smart? Given that the absorption is relatively high, isn't it a possible problem for the layer which contains volatile elements and so on? What is the stability of these complex oxide layers against elevated temperature?
Yeah, it's a good question indeed. Yeah, so be aware that in our case, the PZT is underneath the mirror. So we hope that most of the intensity is already being deflected from the mirror. The temperature is an issue indeed, because typically, let's say, such in some applications, you use some elevated temperatures there, and of course, you also have the elimination of this high intense EUV source there. But PZT can withstand quite some high temperatures. So, for instance, for printing, so like Canon and this OC company does, it is typically done above 100 degrees C or so. So and they, well, that can work quite good. So you have to work on the composition a bit. You have to work on the crystalline quality, but then it can really work at some elevated temperatures.
Nice. Okay, thank you. Some other, there's actually a lot of them, but we probably won't go through all of it. But how did you identify MgO as a buffer layer for achieving PZT epitaxy on the gallium nitrate? That's
very good. Yeah, actually, this was not our work. Then I have to, but this was work done, I think, in Penn State. So they used sputter deposition on the gallium nitride already, and they showed that you could do this MgO trick with MBE type of growth, and we made it to also with PLD. So MgO was not our first guess, but this was just a literature guess.
Good. Let's do a couple more. What is the interface, or what is at the interface of the gallium nitrate and the MgO 111? Is there OMG layer?
Yeah, that's a good question. We don't know yet. So this is something that we are still looking into. I've shown you these EELS maps, right? So electron loss spectroscopy, where you can look at the chemical environment of, well, with atomic precision. And actually, we did not see any deviations in the gallium nitride from gallium nitride, nor from magnesium oxide until we reach this interface. But of course, when you are really at the interface, then also the equipment has limitations there. So far, we did not see anything that there is a real bonding there. But indeed, that's a good question, whether it would be the oxygen or the magnesium or because it's in the 110 direction, right? And if you look at the rock salt there, you could imagine different compositions there. But we did not measure it yet. But it's an interesting question. We like to understand that as well.
Yeah. Perfect. Maybe let's make it the last one. How do you control uniformity and stoichiometry of films prepared on large size substrates? We know that plasma volume has very limited size, right? So isn't that a problem?
That's indeed a problem. This is what we typically do is control the laser parameters quite well. And actually for PZT, it's not a big issue because it's already a solid solution between lead zirconate and lead titanate. And small deviations from the composition will still make it a good PZT material. So for the PZT, it's not a problem. For other materials, yes, it might be a problem. And especially when you also get closer to the edges of the substrates there, where temperature and oxygen pressure control is more stringent. But it's actually having control of the laser parameters that makes the difference. You really need to control the energy density in the laser spot everywhere on the target. And for larger targets, that is more difficult. And so it's a lot of mechanical issues involved there. It should be very stable. But once you have done that, then in principle, because indeed the plasma is relatively small, but the conditions, if you make them similar at every place, then you do not see any deviations from the composition.
Yeah. I was actually informed we still have time till 7 p.m. So we will use as much of your time as possible. So I'll
I'm here. So yeah, I'm here. I'm here.
Perfect. So there's another one. What is the maximum size of the mirrors in the SMILE project? What is the limitation of the size?
Well, right now we designing also a dedicated tool, at least it's on paper, but we want to go to 300 millimeters or so. So, and that's quite a technical challenge. So this is mainly done by the industry. So this is of course not a task of of our group anymore. But of course we are involved. But this is more a technical, logical challenge there. And of course it is interesting for this application. There is not a real high volume market for it. So there are not so many companies that use such mirrors, but it might become interesting for other applications as well. So we'll see. But for now, we only need a few mirrors every month or so. So up to 300 millimeters first, yes.
Is the limitation, yeah.
Well, it's not limitation. We have shown with PLD that you can grow larger, but at least that is the size that we are thinking of.
There are trends to avoid using piezoelectric materials containing plumbum. Have you considered to involve like ILN or other piezoelectric materials in your MEMS?
Sure. So actually, again, I did not have time, but we do quite a lot on different materials also. Potassium niobates and lithium niobates and other compositions, but also aluminum nitride, but then mainly the scandium doped aluminum nitrides. That is a material that shows very interesting properties, and it can be grown quite easily with pulse laser deposition. And there, the thing is that the scandium doping is quite important there. And there, the PLD process is a bit different from spotter deposition. And at least we have shown that we can do this already on small scale PLD systems, but also at large scale systems already. So that's a good question. I think in the future, probably exemption rules on lead containing compounds in EU will be different, and that means that we maybe have to go to lead-free materials there. That's why we are studying quite a lot of different compounds as well. Yeah, good question.
Sure. Yeah. In case of the DUV mirrors, are there many individual pistons for one mirror, or and are they also able to tilt, or do they only move up and down? And
yes.
Is it correct to imagine it similar to a DMD in a projector? Is that a similar technique?
It's good to see that everywhere around the globe there are many clever people. So good to see them. Yes, that's a very interesting question. So yes, there are more individual pistons there. So that has to do with the wavefront correction you need. So typically, let's say for this application, the piston sizes lateral are in the range of 10 millimeters or so, maybe 20. So if you then would have a 300 millimeter wafer, yeah, well, you could almost count the individual pistons. That's enough to do the wavefront correction there. But you can make them smaller. It gets more difficult because you need to control them on the individual base, right? So you need also to have control lines and lines connecting to these electrodes there. But in principle, I think you can do that. And then I think there was oh yeah, tilt. Yes, yes, that's a very interesting one. Yes, we can tilt because what you can do is and you can play tricks with the electrodes, so that means that the applied electrical field might be different on every position. But you also can play around with the geometry. Because of the clamping of the substrate, you can have different types of out of plane movement there. And with that, you can make tilts. There are also MEMS ways to do it. You can also make tilts there. And that's indeed also interesting for, like it says here, for mirror applications in projectors, but even for other applications. So we are thinking about that at the moment. We did not do it so far. We have shown that it can work, but not for real devices yet. That's very interesting. Yeah.
Nice. Question from Professor Pfeiffer. What is used as the feedback for the smart mirrors? In other words, how do we actually know how much we need to bend a mirror part or the pixel?
Yeah. Again, interesting question. These are all discussions that we had in the group also a lot. So I'm happy to share our thoughts about that. Yeah, that's maybe I did not have time to put a lot of effort there. I showed you a few of these strain curves there, so you could see hysteresis in this piston-like behavior. And you either use a feedback control or you try to get rid of this hysteresis. And for the application, it's easier to do it without feedback. So you could do it, you could just measure it. So you can have an optical circuitry to measure it. But for this application, we try to do it without feedback. And that means that there are quite some stringent boundary conditions for this hysteresis, because if you apply a certain voltage to such a piezoelectric actuator in the smart mirror, of course you should exactly know that you dilatated it for 1.4 or 1.6 nanometers or so. We are talking about picometers to nanometers movement of this smart mirror, and you really need to control it. So we do quite a lot on this hysteresis control at the moment. So now we use optical techniques, but we, like I said, we want to go without feedback.
Thank you. Some general question: can you actually keep read control for larger wafers, or are there any issues with that?
Oh yeah, there are many issues. Actually, it's a good thing that if you would go into my lab, you would see a large area system equipped with read. And I think it's standing there now for 2 years or so. Read was switched on, but none of the students ever used it because it's too difficult. Let's say on the small scale, it's relatively easy. Then you have the single crystalline substrates. It's easy to get the electron beam in the right orientation. But if you have a larger wafer, and this is then rotating, so that means that you see this read pattern changing all the time. You have to do timing there. You have to make sure that you're every time you're at the right position. It can be done. We have shown that it can be done. But this large area deposition tool that we are using, we are typically using that for materials like I have shown, like PZT and others. And it doesn't make so much sense to do read control for a micron thick layer. So that's why usually it's not even be switched on there. So it's only was switched on to make these control layers, these single mono layers, to see the crystalline quality there. But that is just stationary, and this is not for real, let's say, thickness control there.
Right, that speaks for itself. Good. Let's go for one last question that we have here before we do the quiz. Do you have any experience with piezo materials in MEMS application in low temperatures? Does it behave then similarly at room temperature, or is that different?
It will change. So yes, actually, we looked into the piezo. It depends a bit on which temperature you are talking about. If you really talk about cryogenic temperatures, of course, there are also piezo materials that can work there, but then you need maybe to work on different compositions. Somewhat lower temperatures, let's say, well, below 0, below 100 degrees, below 0 degrees Celsius, that's still okay. And the reason that we studied it is because some of the materials might show some leaky behavior. And if you cool it down, you freeze in these carriers, and then you have less leakiness there. For instance, in bismuth ferrates and some doped bismuth ferrates, we did that. So yeah, there are a few that can do it, but I do not have too much experience in the piezo properties there.
Mm-hmm. Yeah. Okay.